Okay, now for everyone, I hope you guys received your concept map together with your practice paper, practice question. Now today we'll be looking at gravitational field, and as like for every lesson from regular classes, usually you receive a set of concept map or concept sheet here. Now, the concept sheet is not exhaustive as I hope as I would want it to be. Basically, everything inside the concept map is tested. Everything in the concept map is tested. Obviously, with some other stuff that is being tested as well. So any new things that you come across when you're practicing question, just add on into the concept map. Understand? Okay. Now, for gravitational field, this topic that I would like to start, I want you guys to be able to understand this topic as the best as you can, because the concept that you learn in gravitational field is actually similar to that in the subsequent topic that you will learn called electric field and then magnetic field. So anything that has got to talk about a conservative field, the concept is generally the same. The way you study is also similar as well. Understand? So gravitational field is the start of all the conservative field that you're looking at. And when I mentioned that gravitational field is a conservative field, what do I actually mean? I meant that any energy changes within the field stays within the field, which means the total energy of the entire system will remain constant. If there is a loss, there must be someone gaining that form of energy. That's what a conservative field is. Okay? But what exactly is a field? Now, a field is a region around a specific object of interest, whereby any point inside the field, my object will experience a force corresponding to that field. Meaning to say, if it's a gravitational field, any massive object within the field experiences a gravitational force. If it's an electric field, any charge within the field experiences a electric force. Understand? So a field is basically, it's like, you know, your body aura like that around the object, that anything else that comes inside to this region, it experiences a force. So our entire topic then centralized around what is this force, how to find this force, how to find out what is the strength of the field, so on and so forth. Okay? So under gravitational field, they actually separated your entire topic into two portions. Number one, your scalar quantities and your vector quantities. So you need to be able to know what are your vector quantities and what are your scalar quantities to help you derive values. Okay. Then the next part will be the application part of gravitational field. So the first thing we're going to look at is the vector quantities of gravitational field, and it is then defined by Newton's law of gravitation. So what did Newton actually state in his law of gravitation? And it has already become a law, it's not even a theory, which means it's solidified. It kind of can't be proved, understand? He said that if I have a gravitational field and a massive object or an object, don't have to be massive, a test mass is placed within that field, the test mass experiences a gravitational force. And the value of this gravitational force is directly proportional to the product of the 2 point masses in the universe and inversely proportional to square their separation. Okay? Yeah. So that is basically what gravitational law of Newton's law of gravitation meant. He's trying to relate your force experienced by the object to be equivalent to the product of the 2 masses over the separation between them. However, there is one thing I need you guys to take note of, which is number one. Usually, the mass M1, we take it to be the object's source. That means the mass of the source. Things like your celestial body, your Earth, your planet, your sun, so on and so forth. The one with the bigger mass. Understand? The one that your small mass is being attracted to. Whereas M2, we always take it to be the mass of a small object, a small test mass. Okay? So his gravitational force basically relates the two product of the source mass of the source and the mass of the test mass over their separation, square their separation. But this formula only works for point masses or spheres of uniform density. Understand? So if we are talking about not nice round sphere, then we probably wouldn't use this formula. There's an even more complicated one, just that your syllabus down simplify it for you. Clear? Okay. Now, one thing I need you guys to take note of is number one, G here is not your gravitational field strength. Please do not confuse this G to be the same as this G. This small g here is gravitational field strength. The big G here is the gravitational universal constant. And the value of G is 6.67 times 10 to the power of negative 11. I have a typo in the thing. Can you all add negative to the G? Okay. So being a vector quantity, what does that mean? That means your gravitational force is actually a directional force. That means it has direction. So where is the direction of a gravitational force? It will always be what we call an attractive force. Meaning to say, it will always point towards the center of a celestial body. That's the direction of the gravitational force. Understand? Okay. And because it is a vector, let's say if I have an object, and this object has planet A, planet B, planet C around it, what is the resultant force that is acting on this object? You know, it's attractive force, so force due to A, force due to B, force due to C. And since it's a vector, to find the resultant, we always do vector addition. Vector addition, in short, means vector diagram. So of all the forces that I have here, I'm going to draw a parallelogram or I'm going to draw a triangle law to determine the resultant force. You understand? Okay, so as long as it's a force, remember, draw vector diagrams to determine the resultant. Clear? Okay, so that's the introduction to what Newton's law of gravitation is. The next thing would then be, how do the graph of a force distance graph relate for any massive object in terms of gravitational field? You realize that based on the formula, F is inversely proportional to R squared, which means the force of a massive object obeys what we call the inverse square law. What does the inverse square law mean? The inverse square law means that the greater the radius outside of Earth, the smaller the force. Hence, it's a curve downwards. Inside the sphere, you will get the gravitational force to be linearly related to your distance. That's why you have a straight line graph up like that. But outside, it will follow inverse square law. Because outside, it obeys Newton's law of gravitation. Understand? You don't need to know the one for inside the sphere, because inside the sphere, the gravitational force is defined as 4/3 gm pi density r. This one you don't have to know. But what you need to know is outside of Earth, it follows gravitational law, Newton's law of gravitation, and its inverse square law. So when they ask you to draw a graph relating force over this radius or distance or separation, the curve must be seen. You understand? Okay. So then the next thing they ask us themselves would be, since I now know that the object placed within that field experiences a force, and I know how to calculate that force, can I calculate how much of this force is required to remove just that 1 kg of a substance? Because there are so many objects on Earth or any other planet, and they all have different masses, correct? To put them into a safe basis of comparison, we will use per unit mass. So that's when the idea of gravitational field strength come about. They're asking the question, how much force is required to actually attract 1 kg of any substance? That's it. So then they realize that this gravitational force, a field strength, is distinctive for different celestial body. And to calculate that, it would be taking the amount of gravitational force per unit mass. Now the mass here that we are talking about is per unit mass of your object, which is why if you were to put in Newton's law of gravitation formula, I end up getting Gm1 over R squared. Which makes sense because the gravitational field strength of a celestial body has to be related to that object's mass. It's got nothing to do with the test object that you're looking at. You understand? Okay, so this is what we call the gravitational field strength. Similarly, like gravitational force, it is a vector quantity and it's an attractive force, which means to say, since it's an attractive vector, it points towards the mass center. Okay, and like I said, it's a vector quantity. If I have an object experiencing many different fields, to find the resultant field, all I got to do is just do vector addition or vector diagram. Okay, And you also add the negative sign here for this 6.67 times 10 on negative. Okay, so before we move on to the graphical part, how do we then represent this field strength? Like on a diagram of a planet or whatnot, how do we draw this field strength? This is where we take a look at the lines. Now, every planet, every object will have a gravitational field strength, and that field strength will point towards the center, perpendicular to the surface. And because the surface is circular, that's why you will have a radial kind of diagram to denote the gravitational field strength. You guys understand? Which means to say, nearing the Earth, you realize the gravitational field strength is stronger because the lines are closer. Further away from Earth, the gravitational field strengths are further apart, so therefore it's weaker. And this coincides with the graph. Since G is inversely proportional to the radius square, that's why you can see it curves down like that. You understand? Okay. Following the same as gravitational force inside Earth, G would be directly proportional to my R. So it will increase from the core, it will get stronger and stronger until the surface it starts to curve downwards. Okay, Ken? Okay, but the hard one is not this. Now you have learned two formulas. How do we relate the two together? The two vectors formulas are related by the gravitational force being m times the gravitational field strength. Just multiply with the m, the mass of the object. Okay? Okay, so this is still okay. Now, the hard part is this portion here, G. Your gravitational field strength is not taken to be 9.81 exactly in reality. 9.81 was only because we are talking about Earth. On top of that, we are simplifying Earth to be a very nice sphere, correct? But in reality, my G is not fixed at any point on Earth, purely because my Earth is not a very nice circle or a sphere. It's like sort of like an oblique edge shape. And then the different contours on the Earth's surface causes your G value to be different at every point. So how does the G value on the poles of Earth is different from the ones at the equator? There is a difference. Now let's take a look at pole. Now if imagine I have a block of an object on the pole and I'm pulling it with a spring balance to measure the weight. You realize that the forces acting on the object would be, number one, the weight. Correct? And number two, the tension. Now, as my Earth rotates, what do you realize about the block? As the block rotates, the block is above a sphere. As the sphere rotates, does the block move? No. That means at pole positions, the Earth is not moving in circular motion. You see that? The block is just there. So centripetal force is taken to be 0, and hence there is no resultant force because your centripetal force is your resultant force. Okay? So as such, since my centripetal force is equal to 0, that means my weight should balance my tension. So my weight here is equal to tension. So if I'm looking at the apparent gravitational or acceleration at this point here, which is ma, this is equivalent to mg. If I cancel, this concludes that my object at pole will be falling due to gravity as per normal. Understand? However, if I move now to the equator, so imagine you have a block here now stuck to the equator. There is the weight acting downwards, and then there's the tension acting downwards. So as the object rotates, what happens to as the Earth rotates, what happens to my object? It rotates together. Can you see that? So that means your object at equator follows a circular motion path. And as such, there is a centripetal force. We cannot say resultant force is 0. So if there is a centripetal force, what does that mean? If you look at the diagram, that means my weight is greater than my tension in order to produce a centripetal force towards the center, correct? So therefore, my weight will be greater than my tension, whereby my centripetal force is weight minus tension. So to find my apparent acceleration, which is in my tension is equals to Fc, centripetal force, minus, Fg, your weight, minus Fc. If I were to suck in the formulas here, it means ma, my apparent acceleration, equals to mg minus mac, the centripetal acceleration. So cancel away my mass. What does that mean? That means the new acceleration at the equator is less than my gravitational acceleration due to free fall by my centripetal acceleration. Do you understand? So the difference in gravitational or gravity at the pole and at the equator differ by 1 centripetal acceleration. Okay, this is important. The difference in terms of their gravity is because of the difference of whether or not they undergo circular motion. Okay? Okay, so that will be the 2 vector quantity of gravitational field. Now we move on to the scalar quantity of gravitational field. Scalar quantity, we use energy to explain. So any massive object placed within the field will experience a form of gravity, energy. That energy is known as gravitational potential energy. Now what is gravitational potential energy? It is considered to be a work done. But work done by who? Work done by an external agent to bring my massive object from infinity to a specific point in a gravitational field. But I don't change the kinetic energy. Okay, so what do I mean by that? Meaning to say, as long as my object is at a certain distance away from my celestial body, it will possess a form of energy. That energy is called GPE, gravitational potential energy. Okay, this energy is a stored energy inside your mass, such that the moment you release that object, it will make use of that stored energy and go back to Earth. Can you see that? Okay, that's why work done by an external force. Because this is my Earth. My object will always want to be attracted to Earth. If I purposely don't want it to be attracted, I need to exert an external force and pull it to a certain distance. Can you see that? So that this object will store energy. That energy is GPE. So the moment I release the object will just attract back again, then loses GPE. That's why at infinity, the gravitational potential energy is taken to be 0. Understand? Infinity is taken to be 0 for GPE wise. And the GPE formula is equivalent to negative G M1 M2 over R. That's the difference between the two. Okay? So it's important for you, take note, this one negative also. It is important for you to understand that number 1, gravitational potential energy is a scalar quantity. Being a scalar quantity means to find the resultant, I can only use algebraic addition. Means final minus initial. Things like that. If I want to find a change. You understand? Okay? So I cannot do vector diagram for that, which means I need to include the sign. So for gravitational potential energy, they will always ask you this question. Explain why GPE is taken to be 0 at infinity, or why is it always a negative. You explain by saying that because GPE is work done by external force. The external force is working in the direction opposite to that of my displacement or my gravitational force. Hence, my U is always negative. Okay? So U is always negative because U is always, gravitational force is always attractive. So work is done by the external agent in the opposite direction. Okay? So diagram-wise, how do we represent gravitational potential energy? If you guys take a look at this upgraded diagram, you will see I have my object, my massive celestial body here. Then there is the few lines. Few lines always point perpendicular to the massive object. Then you realize my potential lines are the lines that is perpendicular to the few lines. So you end up having rings of circle around your celestial body. Now, each line represents a potential. Imagine this is 150 volt. This is joules. Okay. And this is negative 75 joules. And this is negative 50 joules. So as my mass move further away from my object, I'm losing more and more. I'm gaining more and more GPE. You see that? Until at infinity, it becomes 0. It should be the other way around. Negative 50, 75, 150. Okay? However, if my object is here at one point and here at the other point, does that mean that I lose GPE? No, I'm still within the same gravitational potential energy line. So even if I'm here, my gravitational potential energy is still -50. You guys understand? I will only lose GPE if I move inwards or if I move outwards in between the lines. Okay, Ken? Okay, so this is gravitational potential energy. Now, how do we actually relate my scalar to my vector quantity? You realize if you look at the formula, F is equivalent to gmm over r squared, but U is equals to -gmm over r. It's somewhat similar, except to change from gravitational force to gravitational potential, I have to divide by an additional radius and I have to add a negative sign. Which means to say that if I were to look at a graph wise and I have a potential energy versus distance graph, negative it together with finding with the gradient will give me my gravitational force. This is the most important one. Understand? I repeat, the negative gradient of a potential energy graph, distance graph, will give you the gravitational force. So questions that gives you such a graph and say calculate the gravitational force, what you need to do is you need to go to your graph and draw a tangent and then you find the gradient, then negative. You understand? Okay. Similarly, compared to that of forces, they want to find how much of energy do I have per unit mass. And that's when gravitational potential comes about. So gravitational potential is just like gravitational potential energy. The only difference is you have this additional mass of the object. So therefore, to relate the two together, there is a missing blank here, I think I can put in, is that the potential energy is equals to the mass of the object times the gravitational potential. And as per what the definition is like, similar to that of a gravitational potential energy, work done, just that I added a new per unit mass. Okay? So work done by an external agent in bringing a small mass from infinity to the specific point without a change in kinetic energy. It's very important that you guys include the word without a change in GP. Understand? Okay? So as per the formula, what does this mean? This means that I have my potential energy divided by mass 2. So since potential energy is G m1 m2 over r, then divided by m2, my potential is just negative G m1 over r. And since it's a scalar quantity, add a negative sign here. It will always be a negative value because of the fact that it's work done by an external force. Okay. Lastly, because it is scalar, to find resultant, use algebraic addition. Clear? Okay, so how do we then relate the vector quantity together with the scalar quantity? That's where we look at the gradient again. You realize the difference between this one here and this one here is such that there is actually divide by, sorry, not divide by. I think I wrote here. You know, change this to multiply, not divide. Multiply by r. The other way around then is divide by r. Okay, so same thing for this one here. From here to here, I'll multiply by r and then I add a negative sign. So obviously, it's not going to work mathematically. More accurate representation would be the gravitational field strength is the negative gradient of the potential distance graph. So if they ask you to find gravitational field strength, draw a tangent, find the gradient of the tangent. Understand? Okay. So that's how we relate all four quantities together. If I want to relate force and gravitational field strength, F equals to mg. If I want to relate potential energy to potential, U equals to m times 5. But if I want to relate the vector to the scalar, then I'll take the negative gradient of the graph. Same thing for gravitational field strength. I take the negative gradient of the graph. You understand? Okay, clear? So one set of questions that they like to ask you is really the technical one, which gives you graphs, gives you ask you to draw graphs, ask you to use the formula. So we'll take a look at that first before we move on to the application-based questions. Now I've given you guys gravitational field questions here. Can you open up the questions? And can you guys take a look at page 5? Daman Hai's question. And attempt the question. I give you guys a bit a while to attempt the question, then I'll go through. It's a pretty long question, but it's a straightforward question. Okay. I go through in another file. Okay, now let's go through this question. It's a relatively okay question. If you understood your circular motion formula well, then you're able to do this question really quickly. Basically, it's talking about Earth as your celestial body, and it's assumed to have a uniform sphere, radius 6,370 kilometers. Take note, this is in km. Okay, and a mass of 5.98 times 10 to the power 24 kg. Now, an object of mass 1 kg is placed on the equator. Calculate the angular velocity of an object. So they want you to find omega. Am I right? You guys have learned before in circular motion, because your object is orbiting around the Earth, so it's moving in circular motion. Omega is equals to 2 pi over t, or 2 pi f. But I don't have the frequency, so I can't use 2 pi f. The only thing I can use is 2 pi over t. Now, what is my period? The question didn't say, but what is one orbit around Earth? 24 hours, 1 day. That's how your period would be equivalent to 24 hours. You understand? But obviously, I can't just use 24 hours because the period given to me has been SI units, so I have to convert it into seconds, times 60 times 60. So this will be your angular velocity. Okay? Now, the next one, it says, calculate the speed of the object. Same thing. Your object is now moving at circular motion. So therefore, in order for you to find the speed of the object v relating to angular velocity, it will be r omega, where r is basically the distance between your celestial body as well as your object's orbit. But not just any distance, must be from the center. Which means to say, if my object, right, is placed on the equator, that means I want to shift this down a bit. My distance between the two objects is therefore equivalent to the radius of the object. So all we got to do is just take my r to be my radius of Earth. However, do you all realize that they gave you in kilometers? So you need to change it into meters by times 10 to the power of 3. Okay. Now, the next one, it says, calculate the centripetal acceleration. So you have also learned before, circular motion, centripetal acceleration is r omega squared. Just substitute in the relevant formula, you should be able to get this value. Okay. All right, now, following the next formula, they say calculate the gravitational force that the Earth exerts on the object. So gravitational force F is gmm over r squared. So I'm just going to plug in the formula 9.83. So these are just a technicality, just substitute formulas, calculate. The only thing you need to take note is make sure all your quantities are in the SI. Okay. All right. Now, following the next one, it says, the object is now suspended from a spring balance. Now, in order for me to be suspended from a spring balance, I need to have tension fixed to a ceiling of a laboratory as shown in the figure. There are two forces acting on an object, one by the earth and one by the spring. So they want you to draw the two forces acting on an object. Now, remember, your object is orbiting around Earth. That means it needs to have a centripetal force and hence a resultant force. So based on my diagram wise, do you realize the gravitational force will be towards the center of the axis, whereas the centripetal force will be away. But because there is a net centripetal force towards the center, Fg needs to look longer than gravitational force needs to look longer than your spring force. Okay, so the magnitude matters. Okay, so once you have drawn the labeled force on the diagram, they say use your answer, calculate the magnitude of Fs. So how do we do that? Remember the question already said that there is a centripetal force causing your object to orbit. So centripetal force is caused by what? Your gravitational force minus your spring force. And your gravitational force is equal to mg. So your centripetal force, which is equivalent to MAC, mass times centripetal acceleration, I can then calculate Fs by taking Fg minus Fc. Okay? And because of this, calculate my spring force to be 9.8. Then it kind of makes sense. My gravitational force was 9.83 Newton. My spring force is 9.80 Newton. So there's this additional 0.03 Newton that acts as a centripetal force. Okay? Okay, as we move on, so these are all still quite straightforward. Now let's move on to the backs where it gets a little harder now. Part C. Define gravitational potential. All of you guys should know how to define this. Is basically given inside the concept map, so you just got to copy and paste. But because there is no energy, so it's just work done per unit mass. Understand? Okay. And then don't forget to mention without a change in kinetic energy. Clear? By answer, you bring it from infinity to that particular point in the gravitational field without a change in kinetic energy. Okay, the next one. The gravitational potential is given as this formula, negative Gm over R. Remember what they are saying? They will always ask, why is it a negative sign? Explain the significance of a negative sign. Things like that. So to explain, we'll say what? It is because gravitational force is considered to be an attractive force. My work done by an external force always acts in the direction opposite to that. As a result, my work done by an external force is moving towards infinity, which is equivalent to 0.
Wait, sorry. How is it opposite? How is it opposite again?
The external force is gravitational force. Let's say this is your planet. The gravitational is this direction, right? External force is always acting in this direction. So let's say if I want to pull the object away from my body.
But isn't the external force like bringing something from infinity to nearer to the planet?
Yeah, but that means your displacement is in this direction. Correct? Because nearing to the planet. But my external force is acting in this direction. So your external force is negative times the positive displacement.
So the external force does negative work?
Yeah.
Yeah.
Okay, so it's a force that is the negative, not the displacement. Okay, done? Now the next question, I think most of you guys should have problems with, because I know most of you guys know that change in gravitational potential energy is mgh. But this question wants you to show that the change in gravitational potential energy is mgh instead. They gave you guys a lot of hints. They said I have a small mass. My mass is near to the surface of the Earth, such that it only moves through a small distance, delta h. Okay? So how do I calculate my change in potential? As per any quantity, change in potential is always final minus initial. So change in potential energy would be final potential minus initial potential. That's what I start off with. Now, then I know that my potential is equivalent to negative GMM over R. So I will get negative GMM over 2R minus GMM over R1. That's the change in potential. Am I right? Now, if I were to factorize out negative Gm or Gmm, you realize you will get positive 1 over R1, which is this one, minus 1 over R squared, which is this one. So then just basic math, if I put them together, what does that mean? R1, R2 over R2 minus R1. Now, what's R2 minus R1? R2 minus R1 is basically your height, the height of the object. When? Because initially, let's say this is my Earth, this is my central, my object was here, so this is R1. Then it increases by a certain height. My object is here, this is R2. So R2 minus R1 will therefore give you the small h. I can change my formula to GMMH over R1 R2. Now, it is said that because h is very, very small, R1 and R2 is approximately the same. Therefore, instead of writing R1, R2, I can write it as GMMH over R squared. Understand? So since I know that G is GM over R squared, I just got to sub this inside here. That's why I get delta dP equals to mg. So a very seemingly simple equation is actually derived from such manner. Understand? the next one for part F, it says here, the planet in E, which means this small sphere planet, this spherical planet here, has mass m and a diameter 6.8 times 10 to the power 3. The product given for G times m is 4.3 times 10 to the power 13. Now calculate the escape speed. So this one you will learn again when we look at the application, but generally when we think about escape speed, think about kinetic energy. So how much kinetic energy must my object possess in order to escape from my planet? To escape from a planet means what? To no longer be in the gravitational effect of that planet. And hence, if when you compare apple to apple, kinetic energy to energy, my KE needs to at least be equal or greater than my GPE, so that I have enough energy to escape from the sort of like clutches of the gravitational field. You understand? So half mv squared would therefore be equivalent to gmm over r squared. That is the gmm over r. That is the minimum. Okay. The half is gone. I brought the 2 up. So then from there, I just got to manipulate the equation. I cancel my same mass, m2, m2. Then I find v squared. V squared is 2gm over r. Then from there, to find v is square root 2gm over r. Then they say gm is given to this value. So all I've got to do is just substitute the relevant values, and then I'll be able to get the answer to be 5.0 times 10 to the power 3. Okay, understand? So meaning my object, right, need to escape Earth's gravitational field, or that sphere gravitational field, if I have enough speed and my speed exceeds about 5,000 meters per second. Okay. Now, so this is theoretical. 5,000 meters per second, theoretically, I should be able to escape if I have this speed. What happens is that when they actually calculated the actual escape speed, they realized that the value needed was actually much higher. Or why is that so? Or it's actually different? Mainly because if I'm actually talking about object being placed on my equator, then I have to understand that there is air resistance present. Okay, I will need additional force to overcome this air resistance. If my object was placed like on outer space, there is no air resistance to talk about, then I don't mention that. But because the question said that the object was at the equator, raised to a small height, so still within the planetary, like what, stratosphere or autosphere. So therefore, I will need to actually attribute energy to overcome it. On top of that, your object is rotating as well, which means to say, initially, your planet is rotating initially. Your object initially already have a KE possessed. When we did the calculation, we assumed there wasn't any kinetic energy at the start. So if we were to account this in, this would give rise to a much more larger kinetic speed. Okay, Ken? So this is This is basically what we need, one type of question that can ask you, really technical, just formula. Okay, now can we take a look at the second type of question that can come up for gravitational field technicality wise, which is the graphs one. Page 12. Page 12, IJ's question. Can you actually no? I rather you guys take a look at this one. There is more graph questions involved for this one. Page 23. It's actually Nanyang's question, but Nanyang's question part A, I don't need you guys to do because it's already what we have went through. Page 22. Can you all just jump straight to part A, part 2, the graph part. Page 23. Yeah. Okay, and can you all attend this question? You know what you did?
Oh yeah.
Then I'll go through the question. Okay, now let's go through the question. Hopefully the graph drawing part was okay for you guys. Now, first things first for this part here, it says, the gravitational potential on the surface of the Earth is given to be negative 62.6 times 10 to the power of 6 joules per kg, and that on the surface of the moon is as this such. Now, why is there a huge discrepancy between the two? Mainly because of the mass of the object. Understand? Next, on the figure, sketch a graph to show the variation of gravitational field strength together with the surface of the Earth. Now, first things first, gravitational field strength is a vector quantity, am I right? Which means it can go negative, it can go positive. Clear? Using the formula for G, gravitational field strength, you realize it's Gm over R squared, which means with relation to the object, your gravitational field strength will obey the inverse square law function. Alright? So now imagine your object here. But my object is moving from this point to this point. Gravitational force is acting towards this point for Earth, towards this point for Moon. That's where the direction of gravitational field strength acts on, correct? So can you see that the gravitational field strength is in the opposite direction as the displacement of your object? And that's the reason why for Earth, my gravitational field strength starts from the negative side. You understand? But for Earth, because the size of Earth is much more massive as compared to Moon, the gravitational field strength for Earth will be much larger. And following the inverse square law function, it bends like that. You understand? Now there will be one region in between the two objects where the gravitational field strength will cancel because there's gravitational in this direction, there's gravitational field strength in this direction. So there will be a point where they both balances each other out. Correct? So that's why gravitational field strength will reach 0 at a certain point. Then following the inverse square law, but now in the same direction as your Moon, you go up like that. So can you see they actually both follow inverse square law, just that one is in the negative region, one is in the positive region. Do you understand? So that is why to draw the graph for gravitational field strength, this is what we have. Clear? Or rather, to draw the force for anything that the graph for anything that is a vector, following an inverse square law, this should be how my diagram looks like. You understand? Okay, take note, the one for Earth is much larger than the one for Moon because of the size difference.
Wait, so why is for Earth negative and yet for Moon positive?
Because your object is moving in the opposite direction as the gravitational field strength of Earth. Imagine you have an object that is moving from here to here.
But the object isn't moving.
No, you take it as, because you want to draw the gravitational field strength variation from here to here. Correct? So you take it that there is an object here moving towards this direction. What is the gravitational field strength experienced by this object?
Sorry, but what if the object is moving in other ways?
Which way?
From the Moon to the Earth.
From Moon to Earth.
Yeah.
Then the diagram will look like that.
No, we don't know which way the object is moving, right?
Yeah, but we are drawing from here to here. You see that? We're starting from this position all the way up to this position. Okay? Because of the arrowhead here. That means that they're increasing distance from this direction. Unless the arrowhead is here, then you will draw it this way. Okay? Okay, then what about the next one? Hence, sketch the graph which shows the variation of gravitational potential. Now, the question here says hence. So you have to ask yourself, how is gravitational potential relating to my G? If you still remember, G is equivalent to what? Negative D gravitational potential over dr. Which means to say, the differentiation or rather the gradient of your gravitational potential graph gives you your G. And you also know that G, gravitational potential, has a formula Gm over R, but negative region. So for each planet, for the one for Moon, for Earth, negative region, inverse square law, so goes like that. For the one for Moon, negative region, inverse square law, goes like that. Now, gravitational potential is a what? Scalar quantity, correct? So we add up the two of their graphs to form the resultant. And that's why we have a minimum point here. Now, if we were to coincide with the one for G, gravitational field strength, do you all realize the point where G is 0, what does that mean? The gradient is 0. So it is a point of maximum or minimum, but in this case here, maximum. Okay? So all scalar graphs would look something like that. You will have a graph because of the first planet, second graph because of the second planet, add them up together, you get a combined graph that looks like that with a minimum or a maximum. Understand, depending on which region you draw. Then why did I draw in the negative? Because gravitational potential is negative. Okay? Can? Okay, good. So approach graph with this mindset, use the formulas, understand that the formulas also give us gradient and whatnot to help you draw the graph. Vector, I can have a negative region, positive region. Scalar, I only belong to one region, depending on the formula. Okay? Now the next one, it says, an isolated sphere spherical planet has a diameter of 6.8 times 10 to the power 6 meters. So it's already in its SI unit, and a mass of 6.4 times 10 to the power 33 assumed to be a point mass. Show the gravitational field strength is given to be this value. All you got to do is just use the formula G equals to Gm over R squared. I think most of you guys should get this answer, right? It's pretty straightforward. Okay, now they say, I have a stone of mass 2.4. This is my small object. And it's being raised through a vertical height of 1008. Now, you realize it's a very short height as compared to the diameter of the Earth, right? Use the value of the gravitational field strength here, the G here, determine the change in gravitational potential energy. So since the height is very small, we don't have to use Gmm over R squared or Gmm over R. All we got to use is just mgh, because the height of the difference change is very small and still near the surface of the Earth. Understand? We explain by saying it this way, that the height of 1000 h is much smaller as compared to that of the radius of the planet. As a result, we can assume that the stone moved through a very small short height with a constant g. Okay? Now, part 3, it says, a rock initially at rest at infinity moves towards the planet, meaning your rock loses GPE, because at infinity it's taken to be 0, then as it comes nearer to Earth, it starts to be negative. At point P, where its height above the surface 3.5 d here, where d is the diameter, so basically you have an object moving towards point P. Point P is 3.5 d away from the surface of the object. Now, it says that the object is initially at rest, then it starts to move, so it starts to gain Ke. Calculate the speed of the rock at point P. Now, because this is a conservative field, what we are looking at is essentially the fact that any change in energy, or if let's say there is supposed to be a loss in certain form of energy, you will gain in some form of energy, or the total energy within the system remains constant. So we can see that at infinity, okay, imagine this is infinity, your rock has Ke and your rock has GPE. But for both of them, it's 0. Because at infinity, the GPE is 0. Then they said that the object is at rest, so Ke equals to 0. Now, as it moves towards Earth, what happens? There is a loss in GPE. Hence, there would therefore be a gain in Ke instead. So to calculate the speed, all we got to do is just use principle of conservation of energy. whereby at the initial KE and the initial GPE should be equals to the final KE and the final GPE. You understand? Then all you got to do is just calculate by cancelling formulas, the similar quantities, then you should be able to get V to be equivalent to this formula here. Now, I want you guys to take note, however, for the GPE portion. At point P, I know GPE is negative GMM over R. But what is R? R is the distance between the two centers, not between the two surfaces. So I have to take 3.5 plus the additional 0.5 here. You understand? So take note, I cannot just take R base to be on the surface, planet of the surface. I need to include the one to the radius. Okay, clear? Okay, now done. Let's take a look at the next part of the concept map, the part at the back, whereby we will look at the applications of gravitational field strength. It's not so much about an application, it's something that you guys already talked about earlier on, because we talked about rotation. It's just that, just take note some of the few keywords. Whenever we talk about an object or orbiting satellite, basically things that is moving around orbit inside a planet gravitational field, make sure you understand that the object is undergoing circular motion. Now, obviously, this means that you need to be able to understand circular motion well. Understand? Because if you don't understand circular motion and you don't master that topic well, a lot of these subtopics, like a lot of integrated topics that put together in circular motion, you will not be able to solve. Okay? Okay, but always remember, when an object moves in circular motion, it has to have a resultant force because the centripetal force that provides the circular motion is the resultant force. Understand? So if I have a satellite, let's say an orbiting body, I can say that my orbiting body's escape velocity is calculated to be Ke greater or equals to Gp. This one we have already learned earlier on. It's pretty straightforward in the sense that the amount of energy that the satellite possesses needs to be able to overcome the gravitational potential energy. Hence, substituting all the random formulas, shifting manipulation, you will get your escape velocity formula. Okay. Now, you might ask the question, am I able to memorize this in the exam and then just regurgitate out the final formula so that I don't have to understand any of those? No, because in the exam, if you just give the last formula and write in values, they will not give you the mark, even though you get your answer correct, because there is no method mark. Understand? Okay, then the answer mark comes together with the method mark. So they want you to show that you are able to derive that Ke is greater or equals to Gpe, then derive this formula out for them. Okay? Second, what happens if I have an orbiting satellite? Now, the word orbiting here straight away means that your satellite is rotating and hence moving in a circular motion. So very straightforwardly, I can just say the centripetal force, which is the resultant force, is therefore provided by the only force present, and that is your gravitational force. So this formula or this equation can help you find a lot of things, because gravitational force is gmm over r squared. My centripetal force, if let's say I want to find the orbiting speed, I just use mv squared over r. Then I'm able to manipulate to get this equation. But if let's say I don't want my orbiting speed, I want my orbiting radius, I can also use mv squared over r, or I can use mr omega squared. Understand? Because they both have r. But let's say I don't want my orbiting speed nor radius, I want my orbiting period. Then I can use mr omega squared, but change my omega into 2 pi over t. And do a little bit of shifting, I should be able to get the formula for period. Clear? Okay. Now, the next one, total mechanical energy. Now, total mechanical energy of a satellite basically means the total KE and the PE of the satellite. We already know that the GPE of the satellite is given to be negative GMM over R. So graph-wise, if I were to do energy versus radius, it will be in the negative region following the inverse law function. Not inverse square, because not R squared. Inverse law function, hence our curve like this. Right? Now, what about KE? KE, you know that it is equivalent to half mv squared. Now, for an orbiting satellite, the V is taken to be this formula here because of centripetal force. So therefore, if I were to sub in, I'll get half m square root gme over r, the whole thing squared. So this gives me half m gme over r. Now, if I put everything together, I'll get GME small m over 2r. Can you see that because of this formula, my KE is positive, so I draw in a positive region and still obey the inverse law function, so curve down. Okay? Now, what is the total energy then? If I add them up together, it's just basic math lah. Common denominator 2r, do the subtraction. You realize that your total heat energy is negative and 2r. So as compared to your GPE, it's half of it. So I'm going to draw negative region below my GPE. So that's how you draw the graph for all three energies for an orbiting satellite. You understand? Okay. It's all derivable by the equation. It's not some extra news. Okay, so what does that mean? That means that for my satellite, the further I am away from my celestial planet, the decrease in the value of the total kinetic energy, potential energy, and hence total energy decrease. That's why infinity becomes 0. Okay? Okay, the next application we're going to talk about is this thing called geostationary orbit. I'm not sure whether you guys heard of geostationary orbit before, but geostationary orbit is the orbit that is in line with the equator. It's a very popular orbit because a lot of countries have sent their satellite to this orbit. Why is it popular? Because these orbits allow your satellite to not leave your sight. Meaning to say, if I'm a satellite launcher, I wouldn't want my satellite to go ahead of me or behind me, because there will be this time delay or time lag, time difference. I want me and the satellite to be orbiting at the same velocity. Can you see that? Now the geostationary orbits allow your satellite to orbit in line with you. So every time you look up, you will see the satellite. Geostationary orbit's property is such that whatever orbital period I have is the same as that of the Earth, which is 24 hours. And it allows your satellite to orbit in the same rotation as that of Earth, which is eastward. Okay, so it orbits in the east direction for geostationary orbit. And it lies above the equator, making it the most popular orbit on the planet. A lot of countries like Russia, China, you want to spy here and there, they send it up to geostationary orbit. But it's getting a little bit crowded because everybody knows the advantages of a good of geostationary orbit. So that's when people are now looking to find out more other orbits that allows them to launch satellite and yet still reaps the benefit of geostationary orbit. And one other orbit is actually your low Earth orbit, your LEO. I'm not sure whether you have heard of LEO before. Probably not. Yeah, but you have heard of Elon Musk before? Probably yes, right? But you only associate mostly him to his Tesla car, right? It's not that well known for that, I mean. But Elon Musk has a company called Starlink. Starlink is basically a service provider, like Wi-Fi internet service provider, his satellite is not at the geostationary orbit. He went to send his satellite to a low Earth orbit. And because it is at that orbit, there is basically not a lot of disruption, which is why when Russia destroyed Ukraine's satellite system, Elon Musk was able to send his Starlink modem or router or whatever you call it over to Ukraine and get their internet for the whole country working without any disruption. And because there wasn't much access to low Earth orbit, yeah, Russia kind of can't destroy that. Okay, so there are many orbits on Earth. If you're interested in that, next time in uni, you can go and study astrophysics. Not in Singapore, we don't really have a course, but maybe overseas. Then maybe you get to work for NASA and whatnot. Okay, can? So that is basically what geostationary orbit is. Just get to know that there's such an orbit that exists that we launch satellite at. So because geostationary orbit is fixed to be a period of 24 hours, using the formula that FC is equals to FG. Can you now see why this formula is so useful? Because it can allow you to find a lot of things. I can then put in my period of 24 hours to find exactly where this orbit is. And plugging in the mass of the Earth, the mass of the satellite and whatnot, a rough estimate of where your geostationary orbit is about 42.2 kilometers away from the surface of the Earth. I mean from the center of the Earth, understand? So it's this particular orbit radius that around the Earth that launches this satellite. Clear? If I want to find the period, I can do so also. Just use this formula to do so. Okay? So what is some advantages of geostationary orbit? Just take note, like what I've said earlier on, geostationary orbits allow you to have a continuous surveillance of your satellite, which means your satellite won't leave your eyes. Okay, and on top of that, it is very far off away from Earth, which means to say I can cover a wider area of coverage. I don't have to send like 10,000 satellites just to look at or just to work for one country. One satellite probably can cover like a pretty huge continental or maybe half the Earth. Understand? Okay. It is also easier for ground station to communicate with them because, like I said, the ground station is in sync together with the satellite. You won't have this part where you will lose the satellite or it's too fast, then you need to chase after the satellite. Get it? Okay, so this is basically what geostationary orbit is about. That's where they apply it in question. But the main application at the end of the day is still talking about centripetal force. Okay, how centripetal force causes your object to rotate around your orbit. And the centripetal force is provided by the gravitational force. You understand? Okay. Okay, good. So can you take a look at the last question for this one here? It's actually the very last question, if I'm not wrong. BJ's question. Yeah. Can y'all try this question? I'll give you guys about 5 minutes to try, then I'll go through. Okay, now let's go through this question here. It says this question is about the factor G, factors affecting G, the gravitational field strength. Takes the Earth radius as 6.38 times 10 to the power of 6 meters. Assume the Earth to be a sphere of uniform density. State an expression of G on the surface of the Earth in terms of the mass, the radius, and the gravitational field strength. So you have G naught equals to GME over RE squared. Okay. This one should be quite straightforward. Huh? Now, next, show that an altitude h, where your h is actually smaller than your radius e, is given to be as such. Now, this one is slightly complicated, but we go it step by step. They even give you a formula here to help you to simplify. You realize that the g at, let's say, at a height here, h here, would be GME over R, but my R instead of RE would be RE plus H, the whole thing squared, right? So if I were to factorize out RE, now factorize out RE means I have to factorize out RE squared. So that means this is how it looks like. I will have RE, and this is 1 plus H over RE. I factorize out RE, yeah? The whole thing squared. So then RE squared, 1 plus H over RE, the whole thing squared. Okay? Then from here, I can group this out, and I'm left with, I bring this whole thing power -2. Then you realize this is similar to this. You see that? So whereby my x is H over RE. So all I got to do is just swap this to be equivalent to 1 minus 2 H over RE. Okay, then from here, G naught is equivalent to this, because that's what I've obtained from the earlier question. And 1 minus 2H over RE. Okay, then using this formula, calculate a value for the gravitational field strength. All you got to do is just sub in the values, where G naught is 9.81, 1 minus 2H over RE. Then you should be able to get a G value to be 9.73. Okay. Now, the very last part, calculate the difference in effective value of G at the equator and at the pole. So, if you guys understood earlier on what we went through in the concept map, you would have seen that the difference in gravitational potential energy, gravitational field strength at the pole versus at the equator is because of the presence of a centripetal force. So, if we were to calculate the acceleration at the pole, it is acceleration due to free fall. But if you were to calculate the acceleration at the equator, it's acceleration due to free fall minus your centripetal acceleration. So since the question says I want the difference in terms of gravitational field strength between the two, that's where the centripetal acceleration constitute the difference in gravitational field strength. Okay, so therefore you end up having calculating your AC, which is basically R omega squared. So since you already have omega, you also have R and your period, then you can substitute the values and obtain your AC. Okay, can? Clear? So hopefully you guys are able to understand gravitational field better. Make use of the concept that you have learned here and use it in the next time to actually go and look at electric field as well, because it's the same concept. Understand? Okay? Okay, so if there is no question, maybe you guys just do a feedback for today's session, then you are pretty much done. Okay, just make a scan the QR code.